Hi everyone. This video is about L'Hopital's rule, which is a way that we can use derivatives to compute some troublesome limits. So you might remember earlier in the course when we were learning how to take limits that sometimes we would arrive at troublesome expressions like 0 over 0 that don't make any sense. And when that happened, we knew that we had to back up and do something different. Usually that meant doing some sort of algebraic trick or maybe even a geometric trick that would help us find the real value of the limit. But sometimes those methods don't work either, and now we're going to learn a method called L'Hopital's rule that will help us evaluate troublesome limits that lead to expressions like 0 over 0 or infinity over infinity. Now, these troublesome expressions, they have a name here. They're called indeterminate forms. And here at the bottom of the slide, you'll see a list of these indeterminate forms, including the ones I just mentioned, and also 0 times infinity, infinity minus infinity, 0 to the 0th power, infinity to the 0th power, and 1 to the infinity power. L'Hopital's rule, which is a limit rule involving derivatives of functions, gives us a powerful way to evaluate some of these troublesome limits. Essentially what it says, modulo some fine print, is that if you have two functions f and g, and if the limit as x approaches a of f of x equals the limit as x approaches a of g of x equals 0, or both of those limits equal plus or minus infinity, then the limit of the quotient of the functions f and g is equal to the limit of the quotient of the derivatives. And this result, it holds also when you use one-sided limits or for limits at plus or minus infinity. So a couple of things to notice here is that this L'Hopital's rule is a rule that applies only to quotients with indeterminate form 0 over 0 or infinity over infinity. And you might recall from a couple of slides ago that there are several more indeterminate forms, and we'll just have to be creative when we use L'Hopital's rule to address those other indeterminate forms, as we shall see in the course of doing some examples. Now, one thing that's a mistake that's easy to make with L'Hopital's rule is, even though this rule involves quotients and derivatives, we are not to use the quotient rule here when applying L'Hopital's rule. Instead, we just simply take the derivative of the top over the derivative of the bottom when applying L'Hopital's rule. In this slide, we seek to provide an intuitive justification for a special case of L'Hopital's rule. On the right, you'll see a graph on the top of two functions, f and g, both of which are 0 at x equals a. So if you take the limit as x approaches a of f over g, you're going to naturally be led to the 0 over 0 indeterminate form. Now, if you look at the graph on the bottom, that's the picture that you might see if you really zoomed in close to x equals a with the top graph. And notice that the blue graph, at least very close to x equals a, has the form y equals m2 times x minus a. The red graph is essentially m1 times x minus a. And now when you take the quotient of those, the x minus a's cancel away, and what you're left with is m1 over m2. But remember, m1 and m2 are simply the derivatives of f and g respectively at x equals a. And that's how, in this instance, you pass from the limit of the quotient of f and g to the limit of the quotient of f prime and g prime. Now we do several examples involving L'Hopital's rule. The first is this limit as x goes to 0 of tangent 3x divided by sine of 2x. And the first thing that we notice about this limit is that as x goes to 0, both the top and the bottom go to 0. So we are in a case where we have this 0 over 0 indeterminate form, and we know that we must be very careful at this stage. In the past, we would have tried to apply some sort of algebraic simplification to clear out that indeterminate form. Now we're going to attempt to use L'Hopital's rule to clear the indeterminate form. So L'Hopital's rule tells me that we should now take the limit of the quotient of the derivatives. So I take the derivative of the top, that is the tangent of 3x, and using the chain rule, what I get is the derivative of tangent is secant squared of 3x. And then I have to go inside and take the derivative of 3x, which is just 3. And then on the bottom, I take the derivative of the sine of 2x. Derivative of sine is cosine. Then I leave the inside alone, and then the derivative of 2x is just 2. And now we ask ourselves about this new limit. And we can see as x goes to 0, secant squared of 3x will go to 1. Cosine of 2x will also go to 1. And so this quotient, this limit of this quotient, no longer is some wacky 0 over 0 thing. It turns into some legitimate number, namely 3/2. So this limit turns out to be equal to 3/2. Our next example is a limit at infinity. We have limit as x goes to infinity of the square of the natural logarithm of x divided by x. So again, we look at this, and as x gets large, the natural log of x gets large, and so the square of the natural log of x gets very large. Meanwhile, the bottom, x gets large as x goes to infinity. And so this is an infinity over infinity indeterminate form, which tells us that we must be very careful here. Sometimes, in the past, we would be able to clear that difficulty using some algebraic method, like factoring and canceling or something like that. But that method won't work here. But we have L'Hopital's rule, which applies to indeterminate forms like infinity over infinity. And so applying L'Hopital's rule, we know that we're to take now the limit as x goes to infinity of the derivative of the top divided by the derivative of the bottom. Now the derivative of the top, using the chain rule, it's 2 times the natural log of x. And then we take the derivative of the inside, namely the natural log of x. That derivative, we remember, is 1 over x. And then we divide by the derivative of the bottom, which is just 1. And so what is that? Well, that's the limit as x goes to infinity of 2 times the natural log of x divided by x. Now we look at that new limit and we see that the top goes to infinity and the bottom still goes to infinity. So we still have an infinity over infinity indeterminate form. And there's no law that says that we can't apply L'Hopital's rule again. So let's try that. we have the limit as x goes to infinity, and the derivative of 2 times the natural log of x is 2 over x. The derivative of x is 1. And now we look at our new limit, and we see that 1 is just staying 1, 2 is just staying 2, x is getting big, 2 over x then must be getting close to 0, and we're able to, we no longer get an indeterminate form, we actually get an answer that this value of this limit is equal to 0. Now we might have expected that from the very beginning, because if you go back and you look at the very first quotient, the square of the natural log of x over x, natural logarithm grows very, very slowly. Even the square of the natural logarithm grows very, very slowly, much more slowly than x does. And so you would expect this quotient to be getting small. For our next example, we look at the limit as x approaches 1 from the right of the natural log of x times the tangent of pi x over 2. Now this one looks a little bit different from the previous two examples because there's no quotient here. We do notice that as x approaches 1 from the right, the natural log of x is approaching 0. Meanwhile, the tangent of pi x over 2, as x goes to 1 from the right, approaches minus infinity. So this gives us an indeterminate form of the type 0 times minus infinity. And therefore, we want to try to apply L'Hopital's rule in some way. But remember, L'Hopital's rule only applies to quotients. So we need to somehow cook up a quotient here that's equivalent to this product. And the way that we can do that is just trade our tangent in for a cotangent. So we're going to let x go to 1 from the right, and we'll keep the natural log of x up here. But remember that tangent is the same as 1 over cotangent. So we're going to have cotangent of pi x over 2. And now we honestly do have a 0 over 0 indeterminate form. And that means that we can try to apply L'Hopital's rule. So if we do that, take the limit as x approaches 1 from the right. Derivative of natural log is 1 over x. And then we have to remember that the derivative of cotangent is minus cosecant squared. And then we leave the inside alone, so we leave pi x over 2 alone. And then we multiply by the derivative of the inside, which is just pi over 2. All right, and now we look at this new limit and see if it's any better than what we had before. Well, notice now that as x goes to 1, the top is going to 1. The bottom, as x gets close to 1, pi x over 2 is getting close to pi over 2, and the cosecant of pi over 2 is just 1. So the top is going to 1, and the bottom is going to minus pi over 2. So that's 1 over minus pi over 2. But when the dust settles from that, we just get minus 2 over pi. And that's the value of the limit. And you can see here that that would be very difficult, if not impossible, to evaluate if you didn't know anything about L'Hopital's rule. For the next example, we have the limit as x approaches 0 from the right of 1 over x minus 1 over e to the x minus 1. And if we look at this, we see that 1 over x will tend to infinity, as will 1 over e to the x minus 1. And therefore, we wind up with this nonsensical infinity minus infinity indeterminate form. And so we need to back up and try something different. Now, we want to try to use L'Hopital's rule, but as in the last example, we need to remember that L'Hopital's rule only applies to quotients, not differences of quotients. So we need to somehow cook up a way to take this expression and turn it into a single quotient. And probably the best way that we can do that is just add this fraction here, find a common denominator and add the fraction. So we're taking the limit as x goes to 0, 0 from the right. And if we use the common denominator x times e to the x minus 1, what we wind up with is this expression in the top, e to the x minus 1 minus x all over x times e to the x minus 1. Okay, now thus far we haven't done L'Hopital's rule or anything. We've just simply written that difference of quotients as a single quotient by finding a common denominator. Now, what happens with the top and bottom of this fraction, this new fraction? Well, as x goes to 0, e to the x goes to 1. 1 minus 1 is 0, and then minus x, that's getting close to 0 as well. So the whole numerator of this new fraction is going to 0. Meanwhile, the bottom is also going to 0, and therefore we're now in a situation where we have the 0 over 0 indeterminate form, and we are in a position to apply L'Hopital's rule. So if we do that, we take the limit as x goes to 0 from the right, and now we take the derivative of the top, which is just e to the x minus 1, and the derivative of the bottom, we need to use the product rule. So this would be e to the x minus 1 plus x times e to the x. And once we're done with that, we stop and reevaluate the limit. The top goes to 0, the bottom also still goes to 0, and therefore this first application of L'Hopital's rule has not cleared away the 0 over 0 indeterminate form. And so we do what we did a couple of slides ago, and that is we apply L'Hopital's rule again. So we take the limit as x goes to 0 from the right, and now the derivative of the top is e to the x, and the derivative of the bottom will be e to the x plus, and now I need to take the derivative of x times e to the x. Using the product rule, that is just going to be e to the x plus x e to the x. And now we see what has happened at the end of the day. Well, the top, as x goes to 0, will go to e to the 0, which is 1. And on the bottom, we get e to the 0 plus e to the 0, which is going to be 2. 1 plus 1, or 2. X e to the x is going to tend to 0. And so the bottom altogether is 2. And so the limit, the final value of the limit here is 1/2. So now we do one of these dreadful limit examples where we have a variable base raised to a variable power. And here we see that the base is approaching 1, whereas the exponent is approaching negative infinity. And that is one of our indeterminate forms, a 1 to infinity indeterminate form. And what we hope to do is to apply L'Hopital's rule here. But remember, in order to apply L'Hopital's rule, we need a quotient that goes to either 0 over 0 or infinity over infinity. So we need to produce a quotient here somehow. And here there's a trick involving the logarithm. So what we're going to do is we're going to let y be this x to the, 1 over 1 minus x. And instead of taking the limit as x approaches 1 from the right of y, we're going to look at the limit as x approaches 1 from the right of the natural logarithm of y. So the limit as x approaches 1 from the right of the natural log of y is the limit as x approaches 1 from the right. And now we take the natural log of y, which is x to the 1 over 1 minus x. And if we do that using the properties of the logarithm, we get that that's the natural log of x divided by 1 minus x. And if we look at that new limit, we see that both the top and the bottom are going to 0 as x goes to 1 from the right. And therefore, we're in a position now where we can use L'Hopital's rule. If we do that, we get the limit as x goes to 1 from the right. And now we take the derivative of the natural log, which is 1 over x. And then we take the derivative of 1 minus x, which is just minus 1. And notice what happens. As x gets close to 1, the top gets close to 1, the bottom gets close to minus 1. And so the limit is minus 1. Now, at this point, we're tempted to think that we're just done. But remember, all we did here was take the limit as x goes to 1 from the right of the natural log of y. What we want is the limit of y. And so the limit as x goes to 1 from the right of y is going to be found by raising e to the power of the limit that we just computed. So that's going to be e to the minus 1, which you can either leave like that or you can write it as 1 over e. And therefore 1 over e is the value of this limit.